Hey everyone! The other day I was asked how I would go about monitoring the network traffic to and from an IoT device on my network. And the person who asked me this had been looking at some pretty expensive network monitoring software. And I said that probably I would look at using some of the excellent tools that all Linux users get for free. And I guess this video is a deep dive into what I would do to monitor an IoT device on my network using Linux. Oh, and it should go without saying, but I will say it anyway, don't do any of this on a network that you don't own, or at least have permission to use, because the authorities tend to frown on it. And with that out the way, let's get to it. I suppose the obvious question to ask at the outset is, why would I need to monitor an IoT device anyway? Aren't these devices, quote, smart? So surely all I have to do is plug them in, set them up, and leave them to it. Well, that's how the industry markets IoT, but reality is seldom that rosy. There are a lot of ridiculously cheap landfill dodging devices out there, tempting people to buy them and add them to their network. People don't stop to think that many of these devices could be so easily compromised that they're also extremely tempting to someone else, and that's would-be hackers. The Open Web Application Security Project, or OWASP, published a list in 2018 of the top 10 attack vectors for IoT devices. Unfortunately, the landscape hasn't changed all that much since then, and while many conscientious manufacturers have really upped their security game, it's more than likely that $2 device you got off a Far East website has cut some corners and displays one or more of these vulnerabilities. Any of the top 4 on the list practically guarantee that your device will have the opportunity to join a botnet, so it can enjoy being part of a few distributed denial of service attacks. So all these vulnerabilities might encourage you to check whether your device, the one that you're adding to your network, is not an attack vector in waiting. On the flip side, you may be developing your own IoT device, and in that case you might be keen to make sure that your baby will, at least, give hackers enough of a hard time that they give up and go and harass something else. I suppose finally that you may also simply be distrustful of a device you've bought. If you're going to add it to your network, you might want to know, does it have a backdoor? Is it hoovering up data about your network to pass on to persons unknown? Indeed, where does it connect to, and what data is being exchanged? This was the essence of why my friend was interested in monitoring a device. So, what to do? Well, ideally, we would get an accredited penetration tester to give our device the once-over, especially if they have OffSec Certified Professional, or OSCP certificates, which require people to actually demonstrate their skills on live machines in order to get those certificates. But these guys are at the top of their game, and quite rightly they don't come cheap, so the next best thing is to use some of their tools ourselves. We can do that by downloading Kali Linux, which is a Debian-based distribution that aggregates all the best open source information security tools into one place. If that's something you're interested in, there are pre-built virtual machine images and ARM versions that you can run on a Raspberry Pi or a Pine 64 board, as well as standard and full downloads. That said, these being Linux tools, we can just run our usual Linux distro and install the specific tools we intend to use, and that is what we will do today. But first, let's get a handle on how networks do their thing, so we know what we're doing and why. At the heart of any home network is the router. This acts as a wireless access point for Wi-Fi devices and a gateway to connect devices on the network to the internet. Also on our home network, we will have all the PCs and laptops that the family use. There may even be an SBC in there somewhere. Then there's the phones and the tablets and the smart TVs and whatever other IoT devices you have connected up to your network. So, what's happening to allow all these devices to communicate and to communicate with things on the internet? Well, back in the day, when networks used hubs, the hub would simply blast out any incoming data to every device on the network, which is why hubs are often called repeaters. It was then up to each device to decide if the packet was addressed to them or if they should drop the packet. Now, the security implications of every device getting all the network data is pretty obvious, which is why no one uses hubs anymore. These days, if you want to send data between two devices, for instance between our phone app and our heating thermostat, our network uses the switch in our router to connect between the addresses of each device. The switch has an IP address, as does every other device on our network. However, our switch doesn't use IP addresses to route data. IP addresses are on the network layer of the TCP/IP model. Switches use the lower level network interface layer to route data, which means that devices need to know each other's MAC addresses to send data to each other. How do they find this information out? They use ARP, the Address Resolution Protocol. A host, like our phone here that wants to send data to our thermostat, will send out a broadcast whois request, essentially saying, whois 192.168.0.22. What's your MAC address? This broadcast is sent using a MAC address of all Fs, which causes the switch to send the request to all the interfaces, except the originator. All the other hosts will drop the frame as it doesn't match their IP address, but our thermostat will respond with its MAC address, which our phone will store in its ARP cache. You can see your own computer's ARP cache by opening up a PowerShell window or a command prompt and typing in ARP-A. We then get a list of IP addresses that are each linked to a physical address, and those are our MAC addresses. The type column tells us if the mapping used was learnt by ARP. These are the dynamic entries, and the static entries are system values. This one here is the broadcast address we mentioned earlier, and these are multicast addresses. The giveaway for that is these 6 digits at the start of the MAC address. Anyway, this is the mechanism that everything on our network is using to send data only to the destination host, whether that's a device on our local network or to the network gateway and onto an address on the interwebs. The problem for us is that we can't see any of that data on a machine that we might want to use to monitor the traffic. If we are going to monitor the traffic, we need to break ARP. We need to stop the traffic going to the switch and interject ourselves into the data flow. We do that with a technique known as ARP poisoning, or more simply as a man-in-the-middle attack. What our listening device is doing is sending unsolicited ARP replies to the target and to the switch. These are responses the target never asked for, saying, "Thanks for asking," and the switch address of 192.168.0.254 has a MAC address of E422.6E44E27A. To the switch it says, "Thanks for asking, 192.168.0.48 has a MAC address of E422.6E44E27A. Now all the data between the phone and the switch will go through the listening device, so we can monitor that traffic. And to experiment with this in practice, I'm going to use a ROC4 board as our rogue IoT device that we want to target. You can of course use a Raspberry Pi or another SBC or even a virtual machine if you want to try this out yourself. But this is my ROC4 C+ running the Debian 11 desktop image, which you can download from OKDo on their Downloads hub. As you can see, this image comes with some default login credentials, so one of the first things we're going to want to do on booting up is to change that password. I've already set up the Wi-Fi and installed the updates, so we're good to go. Now, I haven't used this particular image before, so you may have to forgive me if I fumble about a bit. Anyway, one thing that we're going to want to do straight away is open a terminal. So if we go down to the launcher and applications, let's see, system, and here we go, console. Right then, let's change the password. That's passwd. So the current password is radsa, and the new password, and retype. Okay, so the next thing that we want to do is check our ARP table. So that's ARP-A, and right, let's just try ifconfig, and no. So it looks as though we don't have NetTools installed. I suppose that's not totally unreasonable because NetTools is supposed to be deprecated. But I have to say I do prefer the look of the output on the old school network tools. But there you go, progress. Okay then, let's use IPA to get our network information. And if we go down to WLAN 0, we can see that our MAC address ends in 230D. So let's make a mental note of that, and also that our IP address is 100. And to get our ARP table, we're going to use IPNA. So we have two entries. The top one is another ROC4 board, and the bottom one is our router. And we can see that that has a MAC address ending in F45B. That stale on the end of the top line there, that simply means that the link for that particular ARP table entry hasn't been connected to recently, so we don't have to worry about that. Right then, so here we are on my ROC4 SE board, which we're going to be using as our monitor board. I've already installed the tools we're going to use here, but if you'd like to use them too, you can also install them with the Synaptic Package Manager, and you'll find that under Menu, Administration, and here's the Synaptic Package Manager, so click on that. We need our password, as you're essentially using the elevated privileges you get from the sudo command to install software here. And then you can just search for the software you want using this search box. So for example, if we were going to look for Nmap, which is a super useful network tool, we'd just put Nmap in here. And as you can see from this green square next to it, I have already got this installed. But if I wanted it, I could select it and right click on it. And what I would do is mark for installation. You can see that it's blanked out here because it is already installed. And once I've marked it, I can go up here to this gear icon and click on apply all marked changes, and that would install it for us. And this is a nice easy way to do it, as any discrepancies will also be installed automatically. Okay, then let's close that and open a terminal. Let's move that down there. Now, in between using my ROC4C and coming onto the SE board here, I've had to move my entire setup, including my router. So now would be a good time to actually use Nmap to have a look at our network and see what's changed. And we can do that with sudo nmap-sp, and it's 192.168.0.0 and 24, and that will scan our network. And of course we need our password, and that will take a few moments to go through all the available IP addresses that we have. And there we go, and I can see that we have our router here, and our target board has actually changed IP address to 103 now. That's a good thing we did check that. Good old DHCP, and our IP address has stayed the same, so that's good. Okay then. So another thing that we could do with Nmap at the moment is do a port scan on our target board, and we can do that with sudo nmap-st, and that's 192.168.0.103. And again, that'll take a couple of moments to check all the ports. And lovely. Okay, so if we were to have found some open ports here, we might question whether our device has been set up to allow remote connections from somewhere else. But our target doesn't have any open ports, so that's a good start. So let's think what next. Yeah, I think we'll open Wireshark next, and we can do that with the menu and Internet. And if we go to the bottom, we have Wireshark. This is another essential network tool if you ever want to troubleshoot a network, or if you're just curious as to what's going on the network. But it can be something of a daunting experience when you first run it up. And on this start page, we have a list of the interfaces that we can connect to see what's going on those interfaces. And at the top here, you can see a rather ridiculously named interface. And that's because it's not the built-in wireless interface, it is a USB wireless interface that uses a Realtek RTL88 type chipset. And I'm using that because built-in chipsets don't always support all of the modes of operation that we're going to need. Now, I'm not sure about the built-in Wi-Fi that we have on our Rock 4 boards, but for consistency's sake I'm going to use this USB device because I know it works. If we go up here to this gear-shaped icon, this is our capture options, and we get a list of inputs that we can monitor. And we can also trim down the list here if we want to. It's particularly useful if we have a lot of interfaces. It makes it a bit easier to find the ones that we want. Now, if we go to the Output tab, we can set up a few things that will make catching and intermittent communication more likely. The first thing we're going to want to do is actually save our captures. So we'll give it a name. And we use this browse. I've already got a directory set up, and we'll give it a name. What should we call it? Test.pcapng. Now, to make sure that our file sizes are manageable, what I'm going to do is check this create a new file automatically box, and what we'll do is we'll set it to create a new file after, let's say, 10 megabytes. And what that will do is open a new file every time we get a file of 10 megabytes in size, and it will append a timestamp to that name, and it'll keep going, creating new files until we fill up our disk. Now, on a small home network like we have set up here with only 2 devices on it, 10 megabytes is going to give us quite a long time in terms of network capture. But as we don't have a huge amount of disk space on our Rock 4 board, what I'm going to do is use a ring buffer. And here at the bottom we can set that up. And if we give ourselves, say, I don't know, 5 files, and that'll give us plenty of coverage time. And what that will do is start overwriting the first file after the 5th one is complete, so that we don't actually fill our disk space completely up. Okay, we're almost ready to start. We just need to set up our ARP poisoning tool, and I think we'll use Ettercap for that. And just to be a little old school, let's run this from the command line. But actually, before we do that, I've just thought one of the things that we do want to do is make sure that forwarding is enabled. Otherwise we won't send any of our intercepted communications onto the router. And we can set up forwarding with syscontrol net IPv4 IP forward equals 1. Okay, now we're ready for action. So what we want is sudo ettercap, and we'll do -t, that's for text, -s and -i, and that's our interface, which I will paste in here because that's a silly name and I'll probably get it wrong. And next we're going to want our method, which will be ARP and remote, and we're going to need our router address, which is 192.168.0.1, and we also need our target address, which is 192.168.0.103, and like so. So we're just ready to start now, but what we'll do first is we'll start capturing some network data, and then we will start our ARP poison, but first we'll need a password. And we begin, and we can see a number of ARPs appearing there and looking good so far. And we'll keep recording, and what I'll do is I'll go to my other machine and we'll do a little bit of activity just to give us something particular to record. And what we'll do here is we'll ping, and we'll ping, let's see, 5 times, and we'll do that to Google 8.8. There we go. So now we've got some pings that we should hopefully have intercepted, and what we'll also do is we'll go down to Chromium browser, we'll start that up, and let's just do a Google search for coffee and see what we come up with, and let's pick a page. Well, let's have a look at the Whittards of Chelsea, and we'll go to their page. And okay, so we've got some data there. Right then, let's now go back to our attacking machine and see what's going on over there. And I think we've probably gone on long enough, so let's just stop that and we'll have a little analysis of what we've captured in a moment. Right, so I've stopped the ARP poisoning now, and we're ready to have a very quick look at what we've captured. And it will have to be a quick look really, because a full analysis tutorial is well outside what we can do in this short video. And to be fair, there's no substitute really for training and experience when you're analysing this kind of data. But what we can do is perhaps highlight one or two of things of interest in our feed here. You can see at the top here that Wireshark has date stamped our file name, and if we go down to the bottom we can see that we've captured 4,298 packets, and that was over, let's have a look, going to the bottom here, so just over 50 seconds. It might seem like quite a lot of data, but that's pretty standard for what we were doing in putting a Google search up. So let's have a look at what we've had going on. And I suppose what we could do to start with is have a look at the ARP interactions. We can do that by putting a filter up here for ARP. And we'll do that. And these are our ARPs. You can see that our very first ARP request is from our Realtek Wi-Fi interface. And if we open this up a little bit and have a look at what's going on, we can see here that the opcode tells us that this is that unsolicited reply that I was talking about. And that differs from a standard ARP request that we might find here, look, where the opcode is a request and then that's followed by a reply, as you might expect. Okay, so let's just close that down now. and go back to our data and go back up to the top here. You can see that we're picking up traffic from quite a few different protocol types. We've got TLS, and that's your standard encrypted connection that you'd see on your HTTPS connections to websites. Although this quick protocol here, that's a newer encrypted protocol that's rapidly supplanting TLS on websites. But if you are looking for rogue activity on a network, what you would be doing perhaps is going through these sources and destinations, looking for communications that are going to and from odd destinations. And you can use any of the online whois sites to identify who owns these IP addresses. I mean, for instance, this 142.250 address here, this is a Google server address. And if we keep going down, lots of interaction with Google, like we might expect when we're doing a Google search there. So another Google server there. And keep going down. Okay, well this is a Cloudflare server address. That's probably the coffee site that we were on. And what we're looking for really, I suppose, is servers in more exotic parts of the world that perhaps don't pursue hackers quite like the authorities do here in the West. Actually, another thing that we can look out for is data that's being sent over HTTP. Let's have a little look, see if we have any of that. Now, of course, if it's being sent by HTTP, it's not encrypted. And quite often, hackers can't be bothered with setting up certificates for encryption. After all, why would they? They're stealing your data. They don't really care if it's secure or not. And if they are doing that, you'll at least be able to see what they're taking, as of course it's an unencrypted data stream. But looking at these here, we can see that these connections are to do with Google, the Chrome browser at least. So let's just close that down and go back to the main set of data. And in the end, when you're looking through this kind of data, spotting some nefarious activity will probably require some digging, as your device will probably have legitimate reasons for contacting a number of servers for things like updates or perhaps heartbeat check-ins and things like that. So unless a hacker's being particularly brazen and moving lots and lots of data with HTTP, then it may take you some time to uncover. But we've given you a few hints there of what to look for, and if you want to try doing this kind of stuff yourself, happy hunting. Well, after all that excitement, it's time to wrap this video up, and all that's left to do is say stay safe and see you soon.